In this video, we will discuss the force of gravitation. Yes, I know, we have used the gravity force quite a bit. It's just pointed downward, and it equals mass times g, right? Well, not really. That formula we have been using all this time is just a really good approximation that works when we are on or near the surface of the Earth, or some other planet. But in this video, we will learn the real law of gravity. All objects with mass actually interact with each other through gravity. If we have any two objects, one object will exert an attractive force on the other, which means it is trying to pull the other object closer. In turn, the other object exerts a force that pulls the first object towards it. This satisfies the action-reaction principle. Each object is feeling an equal force pointed in opposite directions. If we were to add a third object to the party, we would see something like this. When I said any two objects, I really meant it. That means that your face is gravitationally attracted to your computer screen right now. However, as we will see later, the gravitational force will usually be insignificantly tiny, unless we are dealing with huge masses, like the kind of masses that planets and stars have. So that computer screen isn't pulling your face towards it in any kind of noticeable way. Not with gravity, anyway. So we see that the direction of the gravity force is on the line that connects two objects. Now let's talk about the magnitude of gravity. Gravity follows this formula. Force of gravity equals big G times the mass of object 1 times the mass of object 2 divided by the distance between them squared. This is a lot of stuff, so let's go through it one by one. First, let's talk about the term on top. Mass of object 1 times the mass of object 2. This term says that the bigger the mass of the two items, the stronger the gravity force will be. This term contains the reason that we feel the gravity from Earth so strongly, but we don't feel anything from things like our computer screen. Now, let's look at the big G. This is just a constant that has the following value. Those units are just the units that will get us units of newtons of force after we multiply G by the rest of the equation. You don't need to memorize this value, but you should notice how small that number is. It's about 7 times 10 to the minus 11. That constant contains the reason why it takes very massive objects to produce noticeable forces. Finally, we have the 1 over r squared term on the bottom. R is the distance between the two objects. This term tells us that the gravitational force gets weaker the further apart the two objects are from each other, but it gets stronger as they get closer. Now, let's actually solve for the acceleration that the Earth feels due to the Sun. The gravitational force acts to pull the Earth towards the Sun, and the magnitude is according to our formula we just talked about. This force will equal the mass of the Earth times its acceleration. Now, if we solve for acceleration, we find that the mass of Earth cancels on both sides, and we are just left with this. So we see that the mass of the Sun and its distance from Earth affects the acceleration of Earth, but Earth's own mass does not. If we flip the problem and solve for the acceleration of the Sun, we would find something similar. Only the mass of the Earth matters, not the mass of the Sun. Generally, when an object is being pulled only by gravity, then its acceleration does not depend on its own mass, but on the mass of the object pulling it. Now that we know how gravity really works, should we ever use the simple F equals mg formula again? The answer is absolutely, and now I'll talk about why it works on or near the surface of the Earth. The force of gravity at the surface of the Earth really equals this whole thing, where the distance is the distance from the center of the Earth to its surface, which is the radius of the Earth. This equals mass times little g. If we look at this, we can realize that the constant little g just equals big G times the mass of Earth divided by the radius of the Earth squared. This is how little g is defined. Now, when we are close to the surface of the Earth, little g does not change much at all. After all, the radius of the Earth is more than 6 million meters. So even if you are 10,000 meters above the surface of the Earth, where planes fly, your distance from the center of the Earth hasn't changed much at all. In fact, if you do the math out, it's much less than a 1% difference. Because that's true, we can say that the value of little g is basically constant, because r does not change much, even at pretty high altitudes. Of course, it depends on what level of precision you need for your problem, but for our purposes, it is almost always good enough to just use mg when on Earth. We use the full formula for when we are in space. In summary, gravity is a force that acts between any two objects that have mass. It acts along a path that connects the two objects together, and it pulls them towards each other. So it is attractive. The magnitude of gravity is given by this formula. We also said that the acceleration that an object feels due to gravity does not depend on the object's mass, but it does depend on the mass of the object that is pulling it. Finally, we can use the formula mg when we are on Earth, but we should use the full equation when we are in space. Thanks for watching.